Hi, everybody. Can everyone hear me, first of all? Cool. My name is Joey Schorr. I'm the lead engineer on the Quay team in New York City. Before I get started, just want to say I apologize in advance. My allergies are a little crazy off the kilter right now, so I may make use of these napkins. And I apparently twisted my ankle, so if I exclaim out in pain, I also apologize in advance for that as well. Falling apart here. I'm here today to talk about better image distribution to worldwide clusters, or, more importantly, to answer the question, why are my pulls so goddamn slow from Europe? So, of course, everyone who's been working in the container space over the last couple of years has had to deal with this problem, even from places such as US East, but especially from places as Europe or Australia or Asia. When you just run, a simple Docker pull, put it behind a time, it could take, minutes on end, and it's very frustrating. And this is a big problem that we wanted to solve on the Quay team. So we thought to ourselves, what can we do to help solve this problem? My talk today will address this issue, show some of the solutions that we put in place, and talk about some of the solutions that we're announcing today, including our BitTorrent support. So, first a little bit of background. How are images actually pulled, and why does this lead to slowdown? So, looking into a bit of the background, container images are pulled from a platform called a container image registry. Quay is a good example of this. A registry implements an API over HTTP for retrieving these images. This is a very important point to keep in mind when we're moving forward. It's really easy to implement an API against HTTP, but it can also be slow due to the number of round trips necessary. In turn, container images themselves are represented in their own formats for each engine. So Docker has its own format, Rocket has the format ACI. Hopefully this will be changing in the future with the adoption of OCI, which will be a nice standard that we can all implement against. But for now, each container engine has its own format. And of course, the format of the images influences the way they are pulled. So for example, if we look at Docker, which I imagine most of the people in the room have used before, we can see that an image is represented as a series of layers. We have some image metadata representing, the actual individual metadata for each of the layers, as well as some blobs representing the file system for each of those layers as tar gzips. This, of course, is just the metadata itself, and then as we walk through, we can see individual tar gzips representing each of the individual layers within the image, forming the overall image that we have. So what happens when I actually go to pull this image? Well, I'm going to issue a simple Docker pull command of some repository, and of course, I have to give it a tag. I'll give it latest. And this, in turn, will cause a number of HTTP requests to recur to the registry. And the big question we face is, how many requests will be made for even a simple image? And why does this lead to slowdown that we have to deal with? So let's take a look here. We have our server on our left, represented as a cool little box. We have our registry Quay on the right. And I'll be keeping a running counter here of the number of requests made when I pull some simple repository. So getting started, the first request made from the machine to Quay is the request to actually get the information about the tag I've requested, in this case, the latest tag. And what will be returned is a list of all of the images in the tag so that the container engine knows which images are necessary to download. Moving on, I first retrieve the metadata for the foo layer. In the previous example, we saw that we had 3 layers. And of course, I also need to retrieve the metadata for the bar layer as well as the med layer. So now we're up to 4 requests, and this is just metadata retrieval. Then we need to retrieve the ancestry for each of the layers. This tells the engine how the layers are related to one another in the ordering. So I do it, of course, for the first layer, foo, and bar, and met. So now I'm up to 7 requests. And finally, I need to retrieve the actual blob binary data, that big tar gzip representing the foo layer. So here I retrieve that, and you can see here it's a big arrow back to our machine because it's a big blob download. And in fact, I have to do this fat download as well for the other 2 layers. So overall, we've actually seen for an image with just 3 layers, I've made 10 HTTP requests. And this really shouldn't be that bad, in all honesty. Except if I'm making these requests across a planet, where we have to deal with latencies not on the order of tens of milliseconds or even hundreds of milliseconds, but on the order of seconds or tens of seconds. So for example, your cluster could be here in this place that we are, perhaps Berlin. And the registry, like Quay, for example, could be on US East. And in fact, this is a real case. And we have to deal with this long latency of pulling all of this information across an ocean, AKA time for sword fighting. Because the number one container programmer's excuse for legitimately slacking off is, I'm deploying. Because it takes so long for me to actually pull all of this data across the internet. But what if we didn't actually have to make more than a single request? Well, I mean, we would have a lot less round trips, which means we'd have a lot less overhead and latency. To address this need, we at the Quay team started working on a feature a year or year and a half ago called squashed images. And the idea of this was, let's take all of our layers and smash them together into one layer. So we go from this, our perennial example we saw, which was 3 layers, and in reality, we usually see images that have far more than 3 layers. And instead, we go to this, which is just one layer with all of the data found in the 3 layers or more, found in just the single layer, also with a shorter set of metadata. And then, what would a pull of a squashed image look like? So, we go back to our HTTP counter here. We first pull the squashed tag, and that returns a list with a single image. It's pretty small. Then we retrieve the metadata for the squashed image, the ancestry data. This will actually be empty, but of course the Docker protocol requires that we still return it. And finally, the squashed layer data. Also a big, fat arrow of blob data, but it's necessary. And this is, of course, 4 requests, but we set a single request. And we want to minimize the number of HTTP round trips because, again, we're pulling across an ocean. Or even worse, let's say we were pulling from Asia or Australia, could be an ocean or 2. So, how do we solve this problem? Well, let's do a little bit more background and see how we at the Quay team addressed this issue. So the Docker CLI actually has a command for loading full images from a single tar gzip called docker load. Each layer's metadata and binary data are actually contained within that single tar, with no additional downloads necessary. So by combining these 2 ideas, we were actually able to come up with this. And this is actually how you use squashed images on Quay today. You issue a single curl to Quay at a special URL, squash. You give it a namespace in your repository name and whatever tag you want, also with some optional auth credentials, and then you pipe it to docker load. And this actually results in a single HTTP request to download all of the information that was previously necessary in 4 or even 10 requests from a normal Docker pull. Thus a single request. So this is great. Now we've basically reduced down our latency quite a bit, and we have the ability to say, serve these images across the entire ocean with just 1 request. But these aren't normal Docker images. These are not the images that we ourselves pushed to the registry, which means that the registry would have to build these squashed images and would probably have to do so for every image. Well, is that sustainable? Fortunately, we found a better solution, and that was the ability to squash images in real time. So we actually spent a lot of time and effort working on the ability to have it so that the registry will just serve images to you, squashed images to you, on their request. And how we do this is actually quite fascinating. If we go back to the format of the images that we saw earlier, we saw the same 3 layers in our metadata. And as we saw earlier, each layer is a tar gzip, and the output, in fact, that Docker load consumes is a tar gzip. And we can take advantage of the fact that these are the same formats to do some really interesting things. So for real-time squashing, we actually start at the top layer, and we emit each file and folder found in the tar gzip for the blob of that layer. We then continue downward all the way to the base layer, and we skip all files that have already been seen or deleted. This is actually a nice property because it means that we're going to be sending less data over the wire further. So we're not only even saving HTTP round trips, but we're actually saving bytes that we're sending across. So if we look at a blown up example of our layer, we can see here we have 3 files that were added: static myapp CSS, static mylogoping, myapp, say a binary, and then a special entry that says I deleted a file. This is actually particularly interesting because Docker only stores entries marking files as deleted. If you delete a file in a base layer that existed in a base layer in a later layer, it'll still be sent along the wire when you do a pull. So that means that if you're doing something like compiling source code, and then you delete the compiler in the next step, and all you need is the remainder artifact, you do a Docker pull, you're still going to be sending that entire compiler all the way down to your clustered machines when you really don't need it. So if you see here, when we're emitting, it's the first layer, so we can just copy the files directly, emit them out into the new tar gzip, and we'll keep track of that deleted file sentinel for future reference. We then move to the next layer in the tree, moving downward, and we can see here we have, my cool package and my static another file. We haven't seen those files before, so we just, bam, emit them. Static my logo, however, is interesting. We already emitted a file at the static my logo path, which is in the first layer, which you can see in purple. If we were to emit it again, it would actually overwrite, but that's actually not the expected behavior. We expected the file at the top layer to be the file we get, and not the one in the middle layer. So we just skip it. And this is also a really nice property of squashed images because, like deleted files, if you overwrite a file in Docker, and then you pull all of the layers down to your machines, you're actually going to be getting all of the copies of that file in all of the layers, even though you frankly do not need them. So by using a squashed image, we can just say, we don't need that layer or that file, and just boom, skip it. Finally, we move to the base layer. So this typically would contain the operating system. So I have user bin bash, I have an etc foobar. And now you can see I have the some deleted file that I deleted in the top layer. And so, since it was deleted, we just ignore it. We don't even send it along the wire. And now you can see that I have created a full tar gzip representing all of the files in all of the layers that I have. But I haven't sent any extraneous files. I haven't sent any deleted files. And I was actually able to do this in real time. So, real-time squashing that saves space. This is pretty cool. Of course, there are a few small downsides to this. Even real-time can have some overhead. So we took it one step further, and we cache all the things. So if you're making if you're doing a pull of a squashed image from Quay, you issue a GET request for that squashed image. We stream the layer data out from the image storage, and then we send back the squashed image. Now, pretty simple and straightforward, but what we actually do is we also simultaneously stream the squashed image to image storage as well. And in this way, all subsequent requests that are made for that squashed image come directly from storage. So instead of having to go and rebuild the squashed image the next time it's requested, we can just return it from image storage as a signed URL and jump right out of the way. And this is really efficient, especially if your image storage, which ours is Amazon S3, has local node caching. So we've gone from 10 requests to a single request with full caching. So this is pretty cool. We've gone from a lot of overhead and latency, and now we've gone down to, single curl, pretty fast, gets everything to you, and then we save it somewhere so it's fast, even faster the next time. So that's squashed images. This was our first attempt at trying to solve the idea of worldwide cluster distribution of images. We launched it last year in January of 2015, and we've actually seen it result in significant performance benefits. Quay itself actually deploys off of Quay, and even though Quay runs in US East, which is literally right next to itself, we've seen deployment times that have gone down by orders of 50% by using squashed images. And in fact, we now have our deployment script run the squashed image pull once to cache it, and then it uses it for all of our deployments. We just replaced our Docker pull with that curl command, and we were good to go. So very easy to use. Unfortunately, squashed images themselves still have a few small downsides, though. The biggest downside, of course, is there's no caching of intermediate layers. One of the niceties of the way Docker pull works is that if you have machines that are going to be pulling different versions of your image and they share base layers, those layers only have to be pulled once. When you're squashing your layers down into a single image, you lose that metadata, you lose those intermediate layers, and now if you were going to be pulling squashed versions of those images onto the same machines, you'd have to pull the full set of data every time. In practice, this is not as big of a problem because we've seen, especially in our own deployments, we use ephemeral machines and a lot of our customers do as well. So there wouldn't be a case where they have the intermediate layers present. But if you're going to be reusing your nodes or you're going to be using something like Kubernetes, this can become an issue. Of course, another slight downside is that the first request is a bit slower because we have to do this real-time calculation and streaming at that time. Simple to work around it. Make a curl request before you do your deployment. But that's a little bit frustrating to have to do. It would be nice if it could be done automatically. And finally, on the list of downsides, Docker load, which actually streams in the tar gzip, can require a lot of memory. And we have seen cases where machines that are have smaller memory footprints can actually run out of memory while doing a Docker load. Docker's done actually some really good work in this field to actually optimize this particular restriction, not for our particular use case, of course, but in general. But there's still been cases where, like, for example, one of our staging machines just cannot load the image because it's running on a low memory footprint. So we thought to ourselves, could we do better? And so we started giving a lot of thought to this, and actually before we could even answer the question, Docker released version 2 of the registry API. So the previous counter that I showed was actually the version 1 API. That was the version of Docker's pull API that was used until Docker 1.6. Everyone who's using a modern version of Docker today against modern registries is actually using V2 or V2.2 of their API. And it actually fixed a lot of the frustrations that we found with V1. So we were very hopeful that V2 would help solve this problem basically for us. Sadly, there were still some problems, and enough so that it led us to have to look into another solution. Docker V2, as a plus, all of its requests are actually in parallel. So instead of making 10 sequential HTTP requests, a good chunk of them are actually going to occur simultaneously. So if you're pulling multiple layers, one layer will start pulling down its metadata at the same time as another layer, and as soon as it has its metadata, it can then start pulling its blob file system. That's really good. There's still overhead, but at least it's, being parallelized. Unfortunately, you still have at least one request per layer. So if you have, 3 layers, you're going to have, at least 3 requests plus one request for the metadata itself. And deleted files are still sent to the client. I should also add that overridden files are as well sent to the client. So while we got some nicety in all the layers being pulled in parallel and the number of requests has gone down by about 50%, we're still going to be sending a lot of data over the wire that we don't really need. And we're going to be having to deal with the HTTP overhead for still a large number of requests. So we thought to ourselves, what can we do to handle the torrent of image data that we're pulling? And yes, pun absolutely intended. And to that end, we started working on a project for BitTorrent-based distribution. And I'm going to be giving a preview of this today. So first, a little bit of background. Why BitTorrent? Before I continue, who here has used BitTorrent in any level of production deployment? A couple of people in the room. Who people have used BitTorrent in other forms of downloads? All right. And who here has some semblance of how BitTorrent works? Okay, so I'm going to give a little bit of background, but I'll go through this quickly. So why BitTorrent? Well, pulling doesn't really scale as we've seen. So let's say I have a node and it's pulling a squashed image from Quay and we get it and no problemo. But realistically, we're not deploying single machines worth of images. We're in fact deploying lots of machines, and usually we're doing lots of machines simultaneously. So if I'm going through a shared pipe to the internet, or I'm going through a VPC, that's going to saturate my pipe very, very quickly. But wouldn't it be cool if machines could share their data? I mean, they're all loading the same information. Why not have them each download a portion of it and share it around? So instead of them each downloading the full image, they could say download 1/3 of the data, and then they can just, share it amongst themselves until every machine has all of the data. And as you noticed, in this part, it's not talking to the registry. It's not talking to Quay across the Atlantic. It's talking to machines that are, microseconds away, if that. Data in cluster, of course, is much faster than remote. It's much faster to take a hop across an Ethernet cable than it is across a fiber, and deal with, Verizon. So, another benefit, of course, is that Torrent also scales well. And in fact, BitTorrent for distribution and deployment today is used by a lot of large organizations. In particular, articles have come out over the past couple years of companies such as Facebook and Twitter using BitTorrent to do the deployments of their software because they're not deploying 5 or 10 or 50 machines. They're deploying 500, 1,000 machines. And even if they were to have dedicated artifact stores inside their network serving this data, when you're deploying 1,000 or 10,000 machines, you're going to very quickly saturate your network to those machines themselves. So, we asked ourselves, how do we adopt Torrent to image distribution, and what are the necessary benefits that we have to address in order to do so? So these were the 3 major points that we came up with that we needed to do in order to make sure that BitTorrent would be useful for those of us in the image container community. It has to be easy to pull via Torrent. Nothing complicated needs to be involved. Ideally, it should be a single command. It must be easy to scale via Torrent because we can't scale, it's kind of useless. And ideally, it should work well with existing deployments. Wouldn't it be great if we could just, take all of our Docker pulls and rocket fetches, swap that one command, and it just works? Well, that's exactly what we did, and of course this was announced a little bit earlier, but we have a new tool called QuakeCuddle. It's available on GitHub today. Support is launching on Quay.io hosted today. Enterprise support will be coming once we've battle tested in our hosted product. One thing I should note is that it's still a preview feature. This means it may break, but we're pretty confident it's working well. And at the high level, QuakeCuddle provides torrent pulling of images. So, how do you use it? Simple. Basically, take your Docker pull or your rocket fetch and replace it with one of these commands. Put QuakeCuddle in front of it. You put the engine you're going to be using, the word torrent, pull, and you just give the image you want to use. It works directly with your image store. In fact, it works so well with the image store that you literally can just replace rocket fetch or Docker pull with QuakeCuddle. To show an example of this, if I do, a QuakeCuddle Docker torrent pull of an image, say the Claire image, it'll call out to download the manifest for the image. Then it'll torrent the individual layers. And then once it's done, it'll load it into your Docker engine for you. And then all you have to do is use it. Same as it'll be there as if you did a normal Docker pull. Run Docker images will be there. Same deal with a rocket fetch. Of course, torrenting isn't very useful without seeding because you want to be able to have all of your machines in your cluster pull from within your cluster. We have it designed so that when you're in the middle of a pull, the system will automatically seed, but pulls should ideally, under this system, be very fast. So we had to make seeding just as easy. And to do that, all you do is replace pull with seed. You give it an optional duration, and at which point it'll terminate automatically. If you're going to have a cluster that is going to be running pretty much until you decide to upgrade it, you can leave off the duration. Otherwise, you can set it to, say, an hour or 30 minutes and then seed for that duration. And it'll do the same process and start seeding those images to your cluster. Now, this is really useful for public images. What about private ones? Really, we want to be able to deploy our private images. Well, QuakeCuddle actually uses your existing Rocket or Docker auth config. So if you want to do a pull, same thing. Just do torrent pull, and it'll read the credentials out of your Rocket configuration for Rocket and your Docker configuration for Docker. You literally can just, credentials are read automatically. You can literally just replace a Docker pull or a Rocket fetch with the QuakeCuddle call, and we'll send the credentials along as necessary. Now, that's great for being able to actually pull the private images, but what about security? Now, we're, of course, at CoreOS very critical about security because that's one of our core mission statements, securing the internet. Well, BitTorrent swarms share peers and data. So what happens if I have my cluster pulling a private image with sensitive information in it? Would that mean is it going to be leaked to the other swarms in the system? Fortunately, no. We added special checks to ensure both privacy and security. In particular, all private images have unique file names. This is actually not just unique to the image, but to the person pulling the image. So if you have a cluster pulling an image over here with one user credential and pulling it over here with another user credential, they will actually be automatically created as separate swarms. They will not share any information. Further, well, and this of course ensures that they have different hashes, even with the same contents, which means that the swarms will not be connected. Further, all private images use signed auth tokens. We actually use a great open source tracker to handle the swarm management called Jahaya, written by one of our engineers. This is actually the same tracker that's used by Facebook to do their deployments. So we knew it was going to scale really well. And the tracker actually has a middleware written such that it validates the token sent for the swarm. And only those with the valid token can actually connect to the swarm for the image. So even though we've guaranteed that the swarms will be separate, we add a further check to make sure that if you request access to a swarm, you have to be who you say you are. That Quay told the swarm, hey, we trust this guy. So the last question, of course, how do we serve these torrents? Well, we took a page out of our book for squashed images. Torrent info hashes are actually calculated for every image when pushed to Quay in real time. So when you do a Docker push today, as that data is streaming into Quay, we have to calculate a hash to verify that we have the data correct. We also just pipe it simultaneously through another calculator, and that calculates the info hash for the torrent. So of course, this is in real time. So as soon as an image is pushed to Quay, it's ready to be pulled via torrent. Torrents are available for every image as soon as they're pushed, public and private. Well, as we saw, you can use QuayCuddle to pull Docker images via multiple layers, but sometimes those layers are going to be pretty small, and you probably don't want to torrent around 32-byte layers that have symlinks in them. So what if we want to minimize the number of calls even further? Torrent squashed images. So let's take our first benefit, combine it with our second, and make it even better. How do we do that? Add -- squashed onto our Docker torrent pull, and it'll just pull down the squashed version of that image in real time via torrent and share it amongst the cluster. So we have a lot of really cool technology we've in here, but really, what's the realistic performance improvements if we're using these pieces of these tools? Well, we've ran some tests. We did some tests on like GCE in Sydney and AWS in Sydney and Singapore and a few other places. And our tests showed a general improvement of up to 40%. And that was without dedicated seeders. If we actually had dedicated seeders in our cluster, we should expect to see much higher gains, because then the majority of the data would come out of the local cluster as opposed to having to follow the web seeds. So, of course, keep your data local is important. Turn this into that using BitTorrent distribution, which is available now, but it's still in preview. And that's some of the stuff we've been doing at Quay to make distribution easier. And I wanted to leave some time for questions. I'm sure there are a few, so if anyone has any questions, please let me know. Sure.
Can you use squashed images when you have signed images, or do you mess up the signature?
The question was, how do you use squashed images when you have signed images, or does it mess up the signature? So one thing I should state is that right now, signing with Docker images is in an experimental preview. So there is, in fact, no way today to use squashed images with signing. Rocket, on the other hand, which is in fact automatically squashed, is in turn signed by Quay's own key. So you have to trust that we are squashing it properly for you. Going forward, squashed images will be treated the same way. We will sign the squashed image with our own key, and you're obviously trusting us that we're not doing anything nefarious there. If you don't trust our hosted platform, we have an enterprise version that doesn't talk to us at all. Any other questions?
Since you are using HTTP for this transmission, why not just use local caching proxy server?
The question was, why not use a local caching proxy server if you're just using HTTP? You could. The problems that we found with using local caching were twofold. First is there's a question of authentication. You want to make sure that when pulls occur, that the user performing the pull has access to the image now. If you have a cached proxy, one machine could have pulled that image and could have had access, and then another machine could come along and try to pull, and that access could have been revoked since then. And now you're in a state, this is unlikely, but it could happen. Now you're in a state where that image has been served to that second machine, even though they technically should not have access. The second issue is one of auditability. Every action taken in Quay and Quay Enterprise is logged to an audit log. So you conduct a pull, and you can always go later and say, oh, who pulled this image? When did they pull it? From which IP? If you're going to a local cache, you lose that ability. With QuayCuddle, on the other hand, when you perform the download of the torrent itself, we log that as a torrent pull. So you still get the auditability benefits without actually having to send all of that data over the wire. Yes?
When will support for the BitTorrent thing be available, or the squash image in Kubernetes?
So we're actually, oh, let me repeat the question first, I apologize. So the question was, when will the support for squashed images or torrent be in Kubernetes? So you can actually today, with some effort, preload images onto machines by just running QuayCuddle as part of a Kubernetes daemon set job. I'm actively talking to the Kubernetes team, and I'm hopeful that they will be willing to accept a proposal which is still very vague for the idea of having custom image distribution objects in Kubernetes. And then one such implementation would be squashed and torrent ability, where you define a third-party object, you put it in your Kubernetes config and say, any image pulled goes through this third-party system. We would automatically not only pull the squashed image via QuayCuddle, but we'd actually automatically seed it as well. And so that would actually be a really nice feature. That's still in very early discussions. You can, as I said, do it today, but it requires a little bit of work.
Okay, and this tracker component, do you need to run it in your own infrastructure?
So we actually do run a tracker for you if you're using the Quay.io hosted product, and it will do all of the auth verification for you out of the box. If you'd like to run your own tracker, you can. All you have to do is run one of the open source trackers. Chahaya, as I said, is open source, and you can just do -- tracker equals on the QuayCuddle command, and that will prevent us from connecting to the public tracker and instead connect to your own internal tracker. You can do whatever you like with that. Similarly, if you choose not to have your machines connect to Quay to actually download the image data, let's say you have a Bastion host that you would like to pre-seed and then have all of your other machines download solely from the Bastion host, you can actually specify no web seed as well on the QuayCuddle command, and it will purely try to use the swarm. Now, of course, if you haven't preloaded that swarm, there's no data, it won't work, it'll just hang. But if you have a Bastion host or host, you could preload those, seed, and then have the others do no web seed. And then we actually will not know at all that you're pulling from us. Yes?
Have you looked at distributed file systems as the backing store for container runtimes?
The question was, have we looked at distributed file systems as the backing store for the container runtimes? We actually have heard of customers doing that. In my limited experience, typically what has happened is when you back, well, at least when you back Docker with a DFS, it's very easy to end up in a state of inconsistency, especially because DFS and file locks don't really go well together. And most of the assumptions made by both Docker and Rocket is that those file locks are consistent. That being said, there's nothing preventing you from trying it. You just have to be careful. Anything else? Yeah?
Have you looked into IPFS?
The question is, have we looked into IPFS for distribution? Briefly, I've actually been mulling over how that might be used, but I have concerns about privacy and security around it. In particular, if you're going to be loading your images with sensitive information into IPFS, how do you make sure that no one else can just come along and take them? Now, the hashes should be incalculable by anybody else, but we're not 100% sure of that. So it's not something I feel 100% confident yet in. In fact, one of the things we made sure to do when we implemented QuayCuddle's torrent support is we actually turned off a lot of the extensions to torrent protocol that would normally be used to share data amongst the swarm. So for example, DHT is turned off, BEP9 is turned off, and so it makes it slightly less efficient, but we wanted to guarantee, and of course all the torrents are marked as private, we wanted to guarantee that there was no way that the data could leak out of the swarm while still getting the majority of the performance benefits. Cool. All right, thanks, guys.